Okay, welcome back everyone, and as I promised, I want to show you some applications of Taylor series. Of course, this will not be covered in the exam, so it's more about seeing the ideas, the rich ideas behind Taylor series, to inspire you a little bit, and just to give you a better feeling about every time you see Taylor series, you know what's the purpose of learning this. Okay. Again, it's a very rich topic. I cannot exhaust them all, so go online and try to Google or search on YouTube for some applications of Taylor series. There are a lot of good stuff there. I will also give you some links for you to watch. Okay, so let's take a look. Of number one is just like what is Taylor series exactly telling you. I'm going to be really quick just for the ideas. Okay, I won't stop and talk about how I got the formula or how I did the calculation. I'm just going to do it. But you can always pause and then try to, go back and try to do the calculations by yourself slowly. But either way, if you have this, basically what you do is you expand them. You have something look like this. Second derivative, second factorial, x minus a to the square, and keep going. So what you're really and remember this one has an interval of convergence. It only works for a minus r and a plus r, where a is called the center. So if you draw something, think about what you're really doing. What you're really doing is you have some function, fx, and you say, hey, I want to pick a center. Let's say the center is here. Then, within a limited interval, a plus r, a minus r, the distance here is exactly r to the left and r to the right. You want to replace this one by a polynomial. That's what you're trying to say. Okay? It only works for this interval. So several interesting things here. If you are going to replace it by an order 0 polynomial, which means a constant, Taylor series suggests you should use fa, which is just this one. So you say, hey, the black line is nothing but this red line. What's good about this? Well, the good thing about this is this one, use the information of your function value. What's bad about it? From here you can see it's really bad because it's not accurate at all. Or you can say it does not use the information from all the other derivatives. So how do you use the other derivatives? Well, Taylor series suggests what you should do is you can use the order 1. This time you can use a straight line. Then don't draw any random straight line, but draw the one, have this format, which means not only the line past this, but this line also share the first derivative with the black line. So this is my approximation if I use a linear one. Now, not only I retain the information of the function, I also retain the information of the first derivative of the function. But I don't have any information about the second derivative, third derivative, because if you use a line, the second derivative is basically 0. It's no information. So how do you do better? A better way to do it is to use a quadratic. To use this. Then there is a restriction you want to put on this quadratic. Number 1, this quadratic should pass this point. Number 2, this quadratic also has a derivative here. You want to make sure the quadratic you pick have the same derivative here with the black line. Number 3, because it's quadratic, you can in addition require they have the same concavity, which is a second derivative with this line. So you have something like this. That's the quadratic you're going to pick. Okay. Now from here you can see every time you add the order of the polynomial you have, you use additional information in the derivative. If you take an order 2, you use the function value, you use the derivative, you use the second derivative. Add one more, you use the third derivative. Add one more, you use the fourth derivative. So if you keep adding until infinity, then not only your red line here is going to share the function value, it also shares the derivative of this black line. It shares the second derivative of this black line. It shares the third derivative of this black line and all the derivative of the black line. Then we can basically say this red one and the black one are exactly the same. That's kind of the logic. Okay? With that in mind, this is pretty nice. But if you think about it, that's the first good thing. The second thing you should think about are this. What you're trying to do, you try to pick an interval. Okay. Then you try to say, I'm going to approximate all the function value here, which is not at this center, by the polynomial, not the original black line. And I want to have a good approximation. Okay. Now, when you try to do this kind of replacement, you use Taylor polynomials. But note, when you use Taylor polynomials, what you use are all the information happening at this single point. So what you're trying to say is, I'm trying to predict what happens close to this point using just the information from this point. Okay? For example, I'm trying to predict tomorrow, the day after tomorrow, the day yesterday, and the day before yesterday, all using the data I collected from today. Okay. Then, just knowing the value of today, which is FA, may not be a good approximation. I probably also want to know how I'm going to change today. That is F prime. Or you have even more information, so you exhaust all the possible informations at this single point. That will enable you to predict everybody which is not at here. That means you can predict what's going to happen tomorrow. Okay? Or not in the too far of the future. So that's another good advantage of Taylor polynomial. That is, if you use all the informations, which means all the possible derivatives of this single point, you can predict a little bit what's going to happen close to it. If it's a nice function, your interval of convergence can be really far. If it's really a bad function, then there's not much you can predict because your function changes dramatically. Okay, that's what you're trying to do with Taylor polynomials. The third thing is, in general, Taylor polynomial, if your function is not too bad, that means your function derivative is not too bad, your Taylor polynomial can converge really fast because of this factorial. Okay. And it's very easy to think about then. To approximate a general thing, maybe usually people just need the first three terms, which means a quadratic. Why? If you think about this in physics, this is location, right? Then this is nothing but velocity, and this is nothing but acceleration. So if you want to study any kind of motion, you take a point, you say, hey, at this point, not only I know where you are, I know your velocity, I know your acceleration, I'm going to try to predict what's going to happen before and after. Okay. If your motion is not too irregular, like some motion like this, which is really ridiculous, right? If it's as smooth as this, that means you can replace it by another nice motion, which is the Taylor polynomial, which is quadratic. But this motion will share the same location. It will share the same velocity. It will share the same acceleration as your current motion right now. Are they the same motion? No. But if your motion is not too bad, they will be very close because you have all the essential part of a motion. So even just a second order Taylor polynomial can give you a really nice approximation due to how fast this one converges because of this factorial here. Another thing you can think about is actually this term here. This term is some number to the nth power, so it will be really nice if x minus a is less than 1. That means you're going to take, for example, 0.2 to the nth power. That means this one also help a little bit to make the number small. Okay, that means it's going to converge really soon. For example, 0.2 to the 10th, you can basically ignore this term. That means starting from the 10th term, you don't really care too much about what happened after that. That basically tells you your x and a should be close. Okay? That means if you take a function, you take this center, you try to approximate it with a polynomial. Then, this one basically tells you the closer your x are to this a, you have a better approximation. If you're too far away, the approximation is going to be way off compared to the closer ones. So that's another indicator to tell you, okay, what the center does. The center basically tells you which information do I use. If I use the information here to get a better approximation, you better approximate the points which are close to you, not the points which are far away from you. So if you know everything about what happens today, you probably can predict what's going to happen tomorrow at 1 o'clock. Now, if you want to predict what happens at noon tomorrow, it's going to be a little bit more off. And if you're going to try to predict what's going to happen at next week, it's going to be way off, unless you take a lot more information, which means are the terms in the Taylor polynomial. Okay? So that's the idea of Taylor polynomial, or Taylor series. It basically takes a function and try to approximate it using all the informations, which means derivative, second derivative, third derivative, and all the informations of derivatives at this point. If you exhaust all the possible derivatives here, that means you actually know a lot for points around here. That's what we're trying to say. Okay? The better, the smoother the original function, the better the approximation. Therefore, you can have a very big interval of convergence. If you know what happens here, if the motion is regular, you can probably predict for time really far from you. But if you have a really irregular motion like this, knowing something here, it's really difficult for you to even predict what's going to happen here using the information here. Okay, so it really depends on how good the original function is. That's why e to the x is the best. The interval of convergence is negative infinity to infinity. Okay, now given an idea, let's try check several applications. The first one, I'm just going to restrict it to something we can do so far. Okay. The first one will be really interesting or really easy. That is just approximate numbers. Now, what is e squared? Right? What is e? What is sine 0.3? You know, when people do those kind of things before, what you do have is actually a trig table. You have a big table. It tells you for 1 degree, 2 degrees, 3 degree. Okay, what are the value of sine, cosine? The problem here is how did they get all these kind of things, all these numbers here, which are really small digits, okay, with a lot of decimal places. The first time people did this, they basically used really nice measurement equipment to measure the sine and cosine. So if you know that it's 1 degree, you basically make a big triangle. You try to measure how long this is. You try to measure how long this is with a really precise ruler, and try to get the number here, which you can see it's not reliable at all. Now, if you think about how do we generate those kind of table, it's pretty easy. What you need to do is, for example, let's just take e to the 2. You know e to the x is this. Okay, again, I'm doing things really fast here. If you get confused, go back, pause, and see how I did the computation. Okay, that's the Taylor polynomial, Taylor series. And then we just say, well, we know the error estimate, so we can stop somewhere and just say this. Okay, then they're not the same anymore. It's approximately 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. And we throw away all that, and let's assume the error is already under control. Remember, we can calculate the error technically, so you can actually estimate to get a certain precision how many terms do you need. But let's just say we stop here. Then what is e to the 2? I'm not going to give you the best number, but I'm going to give you the best number I can have with this approximation. From here we can say it's 1 plus 2 plus 4 over 2, which is 2, plus 8 over 6, plus 16 over 24. Okay. From here we can see for any function, as long as you have the Taylor polynomial, all you need to worry about is how to do the multiplications or the power, which is not hard at all. So let's take out a calculator and try to calculate this. 1 plus 2 plus 4 over 2 plus 8 over 6 plus 16 over 24. Oh. That give you 7. Okay, we got lucky. And then what's the real value of e to the square? It's 7.389. So it's not the best approximation, but you can see we're pretty close. Now how to make it closer? Just add one more term, x to the 5th over 5 factorial. If not happy, x to the 6th over 6 factorial. Well, just keep going and keep going and keep going. Eventually you will find this one converge really fast because of the factorial here. So you won't need much. I would say 10 terms, it will give you something super accurate. So in this way, we can actually calculate any value of e. What about sine 0.1 degree or something like that? You do know the Taylor polynomial, right? And you can stop anywhere. Plug in 0.1 and just get the value of this. You will not be too much off, as long as you make sure this one stays close to the center. Okay? Because this one is actually centered at 0, right? Okay? So what about ln x? For example, ln, I don't know, 3. Again, we do know the Taylor series of ln 1 plus x. Check the notes. And then all you need to do is just finish the Taylor polynomial, cut it somewhere, as long as you're happy, and then plug in 2 in order to get ln3. And then everything left is just compute a polynomial. So you can approximate a lot of functions in this way, as long as you know how to calculate the derivatives. At least for things like that, we cannot do before. For things of sine, cosine, we cannot do the thing before. But now we can make this table by ourselves using polynomial. Moreover, we don't need to rely on how good our ruler is. We also know how big the error is because we do know the error estimate for Taylor polynomials. So that is really good. Okay. Another thing you can think about is, what is the square root of 3? I will leave it for you. What you need to do is take the Taylor expansion of square root of x. You don't want to do it at x0 because when you have 1 over square root of x as the derivative, you do not want to plug in 0. So just do it centered at 1, which will make the derivative really easy to compute. And then when you finish, you just plug in another number 2 to get, you just plug in number 3, and it probably takes 3 or 4 terms from the Taylor expansion. You will be able to actually calculate square root of 3. By the way, it's 1.732, roughly something like that. So you can do all these kind of things already. That is the first application. Okay, as long as you know how to do polynomials, you basically know how to do all the other weird functions like square root, sine, cosine, e. You're not going to do it accurately, but you will have an approximation. The good news is the approximation can be as good as you want as you take more terms. Plus, you have the error estimate, so you know how big the real error is going to be. That's really relieving. Another thing, maybe you didn't thought about before, but which is really interesting. What is pi? Pi is 3.14 something, right? But how did the people get this number? There are a lot of ways, but I can introduce you an interesting way. What is Titan pi over 4? It's 1, right? That means pi over 4 is arctangent 1. That means pi can be approximated by 4 times arctangent 1. But you don't know arctangent 1. Good news is, you do know arctangent x, and you do know this one has a power series, which is -1 to the n, x to 2n plus 1, 2n plus 1. We get it from 11.9. You try to take the derivative to get this one, get the formula, and take the antiderivative. But either way, this is the Taylor polynomial of arctangent, which is 0. So x over 1 minus x cubed over 3 plus x5 over 5 minus x7 over 7, and keep going. That is arctangent x. So what is arctangent 1? That is going to be 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, and keep going. That's it. 4 times this is going to give you pi, because this comes from arctangent 1, which is pi over 4. Now all you need to do is just select a value. I'm just going to say, hey, I'm going to stop here and use a calculator to tell you 1 minus 1/3 plus 1/5 minus 1/7, okay, equals a number. And then use this number to times 4. And what you got is 2.89523, which is still off from here. But you know what we're going to do? We're going to keep taking more and more terms. But from here you can see, because of the special way of this one is constructed, you don't have a factorial here, so this one may converge really slow. Even for very big n, the bottom is probably not too close to 0. Okay? But if you have a factorial, the bottom is just reduced like dramatically. Not before long, the whole thing will be adding almost like adding very small numbers, so you can start to just toss out all the terms. So I would say for this one, do more terms, and try to see how many terms do you need in order to get 3.14. Moreover, you do know how to do the error estimate of Taylor polynomials. But this is just one way. Okay? You can also do arcsine 1/2, which give you pi over 6, right? And then just times 6, you will have pi. This one, you'll need the Taylor expansion of arcsine x. Okay. You can also do cosine. You can do all the combinations. I will give you a paper to let you read. And then you will see actually you have all kinds of ways to do this. And some of the method converge really fast. You only need probably 7 terms. You got a really nice precision. Some of them may require a lot of terms like the one I just showed. But either way, we can do it. Okay, so that's the first thing. Now let's check the second application, which we may have, which is related to our class. Okay, let's think about how to do this one. That's an integral. Well, I just put this one here, but any function will work, the method. Okay, how to do the integral of this one? Well, you need to do integration by parts. Okay, for something slightly more complicated, it's going to be difficult for you to do integration by parts. So it's going to be difficult in general. But now what you can do are the following. Again, I'm not going to pause and say too much. I write down all the procedures. You go ahead, pause if any steps just troubles you, and try to take some more time there. I'm going to define a fx, which is the integral of this thing. So fx is going to be from 1 to x ln t dt. This implies f prime x is actually ln x. Then this one, ln x dx, is nothing. Oh, not 0. We want to know what this is. Is nothing but f2 minus f1. Actually, it's just f2. All right. So now our job is try to find what is f2. That will be the integral of this. Now what is f2? Well, let's find out fx. Using the Taylor expansion, fx equals fa. Let's just do Taylor series at a equals 1. Then this one is going to equal to f1 plus f prime 1 factorial, okay, x minus 1 plus f prime 1 2 factorial x minus 1 square, and dot 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 dot. That's the Taylor expansion, right? Okay. Now fx is this. Okay. F prime x is this. F prime x is going to be the derivative of this, and f prime x is this, and f prime x is going to be that. And maybe just one more term. Okay, if you want, you can do more. But I would just say, remember, eventually we want to stop somewhere. We just say, I'm just going to use everything I have so far. Okay, I will have some error, but I don't care. So, what about if you plug in 1? Okay, 1, -1, 2, and -6. Okay, with all these here, now I can write down fx equals, and f1. f1 is when you plug in 1 to here, that gives you 0. So fx equals 0 plus 0 plus 1 over 2 factorial x minus 1 square plus, so minus 1 over 3 factorial x minus 1 cube, okay, plus 2 over 4 factorial x minus 1 to the 4th, minus 6 over 5 factorial x minus 1 to the 5th. Okay. Now that is my fx. That is not equal, that's approximately, otherwise you should keep going, okay, but we don't. Then, what is f2? Which is the integral we're trying to look for. It's going to be 1 over 2. 2 minus 1 is to give you 1. 1 squared give you 1. Minus 1 over 6, which comes from 3 factorial, plus 2 over 24 minus 6 over 120. According to the formula we just did, Remember, this is not accurate. This is the approximation because you throw away all the terms after that. But nonetheless. The answer we got is 0.367. Okay, that is our approximation. If we choose to use 5 terms, we can certainly use more. Now, how close are we to the real one? Well, let's use a calculator to find out what's the real integral. Or you can do integration by parts. The real one is going to be ln4 minus 1, which is roughly 0.386. So you are 0.2 off, roughly, 0.02 off, which is not too bad. And you can always improve if you just take more terms, which I think is not too hard to do. So try it. Try to do 2 more terms. I didn't try it myself, but my bet will be it's going to be really close if you just do 2 more terms. Okay, so what did we just do? We try to do an integral. In real life, the integral can be really hard. Maybe you use integration by parts, partial fractions, all the fancy stuff, and you figure out this is really difficult. It's difficult, but then what we did is we actually defined the antiderivative to be fx, which we don't know how to find. Okay, we don't want to do the integral. But then we just do the Taylor expansions of this antiderivative. What you have is this one will always be 0 because you start and end at the same term. This one will be this one here. You don't have to do anything but copy it. So you actually avoided taking the antiderivative. Instead, you take a lot of derivatives. And as far as we know, derivatives are way easier than antiderivative in general. Then we stop somewhere. We use a polynomial to approximate the real one. And again, we can do the error estimate. So if we really want, we can figure out, in order to get a certain precision, how many terms do we need. Okay. But we don't do any integrals. Instead, we do derivatives and polynomials. Okay? That's the beauty of Taylor expansion. You can do this for any integral. This is called a numerical integral. And this is the only one way of doing it. Okay? But that's actually how computer does stuff. Because computer can handle polynomials, plus computer can only handle finite terms. But computer don't know how to do integrals easily. Okay? There are ways computers can do integrals, but that requires very, very abstract coding. So we try to skip that. And even for very complicated functions, the computer simply cannot do the antiderivative. But they can still do those kind of approximations. So that is good. And the third application, which is the last application, can be a little bit long. We want to talk a little bit about the numerical derivative. Let me again write down this. X minus a plus f prime prime a 2 factorial x minus a square. Okay. Dot, 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 dot. Now what I want to do is I want to plug in x equals a plus h. What's going to happen? Well, I'm going to replace this by a plus h. But I'm going to replace this and all these by a plus h. But note, x minus a equals a plus h minus a, which give you just h. And this h is going to be super small. I will show you why I need this later. But then if I rewrite everything, this is a plus h equals fa plus f prime a over 1. I'm just going to do it. X minus a is a plus h minus a, which is just h. F prime prime a 2 factorial h square plus f a 3 factorial h cube h fourth, h fifth, h sixth, whatever. They just keep going. Good so far? Here is where the magic happened. Okay, let's take this fa and then minus it on the other side. so far? And then let's divide it by h. This gives you f prime a divided by h, so this h is gone, plus f prime a 2 factorial h squared, but now you have one h divided, it's h, and then h squared and h cubed, because before you have h cubed, h fourths, now they become h squared, h cubed. Dot, dot, dot. Everybody is still a polynomial of h. Good so far? What is this? Take a look. That is the difference quotient. That is definition of derivative. How do you define f prime a? F prime a is I take a point away from it, do this, I found a straight line. All right, and then what happened to do the, the instantaneous rate of change? You let this point go closer and closer and closer and closer, and you eventually have a tangent line, right? So you let h goes to 0. That's your definition of your derivative, which comes from the slope of a tangent line, which means when h goes to 0, your second line basically becomes a tangent line. But now if you think about Taylor polynomial, what's going on here? Think about it. What's going on here is these two are not the same. But when you let h goes to 0, everybody after this will be gone. Then these two will be the same. So from Taylor polynomial, you actually have the definition of the derivative showing up. Moreover, in real life, when we do this, we actually don't let h goes to 0. We just let h to be small. Let's let h to be 0.01. Okay? And then use a computer to calculate it, and we say that is roughly your derivative. Because we cannot actually get the accurate derivative when things are complicated. Make sense so far? Then what we're definitely going to have an arrow. It's not the real derivative. It's just an approximation of the derivative. But using Taylor polynomials will tell you how big that arrow is. The arrow is exactly this. And when you let h goes to 0, the arrow is gone. So basically, using Taylor polynomials, you have the definition of the first derivative. You also, in addition, have the error estimate, which is something we cannot do before. We only know the smaller the h, the smaller the arrow. But this one tells you how the error actually varies by h. For example, if h is 0.01, probably you can now calculate the error is roughly 0.03. That is huge. Okay? Why? Because in real life, usually you don't have continuous, actually you never have a continuous data. You may think in real life if you see the temperature, you will have something like this, but no, you don't have the temperature like this. You only have the temperature measured every 10 minutes or something. You have data points like this. Make sense so far? And then what you say is, even though I don't observe it, the real function, I don't observe it, but I assume in real life there is a real function. Now I'm going to approximate what's going to happen for this one using all the samples I collected. For example, then, I want to know what is the derivative? What is the changing rate at here? Knowing only my samples. What you would do is, if I put it here, you basically take this point minus this point, and then you try to find the slope of this one. You say this is going to be the derivative of the original function here. Then, of course, it's not accurate because your sample from the beginning is discrete. But with this, you can start to tell how big the error is. And that is huge. Okay? Sounds good? Okay. And here are some interesting things you can do now. I will just show you two examples. The first one, this totally makes sense, right? Okay, for example then, in real life, let's say we want to know the derivative of x to the cube, okay, at x equal to 1. I'm using simple functions to just show you the idea. Okay. We know the real value is going to be this one prime is 3x squared, so the real value is going to be 3. That's the real value. But now what we're going to do is we're going to take a calculator and approximate it, and then we're going to pick h equals 0.1. Then it's really easy to do. That's going to be f1 plus 0.1 minus f1 divided by 0.1. which is 1.1 cube minus 1, which is divided by 0.1. Use a calculator. You will find this is going to be 3.31. Okay, this is not too bad because the real one is 3, and you are more or less the same. Now, to make it better, you can just take h to be 0.01, okay, and so on. Good so far? So eventually, if you take h to be really small, you will get closer and closer to 3. That's what we had before. Okay, the idea comes from here. Let's say this is 3. Probably this is not a good graph. Whoa. Then what you do is you take 3, you take a little bit after that, you draw a line, and you say, hey, the slope of this one will be very similar to the real tangent line here. Sounds good? Okay, that's what we're trying to do. But now, I propose another way of doing it. Okay? Another way of doing it is I use this one. Okay? Take a look. This is called central difference. And this is different from what we have here. Now this time what we do is, instead of taking 3 and go a little bit ahead to 3.1, okay, I found the slope of this. I don't do that. Instead, what I do is, okay, let's use 3 plus h. Oh, sorry, this is 1. And 1 plus h. Okay. Let's use 1 and 1 plus h and 1 minus h. So instead of using these 2 points, which is 1 and a little bit behind 1, what we do is actually we take the point before 1, we take the point not here, and we choose to not use the information here. Instead, we take the slope of this instead. From here, you can see it's fa plus h, fa minus h. Okay, and the whole thing here become 2h because you guys are 2h away from each other. Number 1, as you can see, as h goes to 0, this one will also be like very close like this. So eventually this one will be the same as tangent line, right? But now my question becomes, which formula is better? In other words, which formula give you a smaller arrow given the same h? Right? If you do h equal to 0.1, I must also do h equal to 0.1, otherwise I'm cheating, right? So if we both take h equals 0.1, which formula will give you a more accurate result? This one take a shorter period, this one take a longer period. This one use the information happening exactly at 1. Remember, we're looking for the derivative at 1. This one actually don't use the information at 1 at all. Instead they use the moment before and the moment after. Which one is better? Pause the video, make a guess, and somehow came up with a reason. Okay, and if you come back, let's just do the calculation. F prime 1 is going to be 1.1 cube minus, now going from 1, go 0.1 to the left, that give you 0.9 cube, divided by, before that was 0.1, now you do 0.2. You don't do 1, you do 0.9, because it's before. This is going to give you and you can calculate it by yourself, divided by 0.2. That will give you 3.01. Okay. Remember, the real value is 3. The first formula give you this, the second formula give you this. Now, at least from what we observed for this particular function, using the same h, this formula is better than this formula here. That means if you use a calculator, you use a computer to calculate the numerical derivative of this thing, you better go with this one instead of going with this one. Okay. That means to get, for example, if you get the temperatures of every single day, to get the changing rate of the temperature today, here, Instead of using the tomorrow's temperature minus today's temperature, that's the change. You should use tomorrow's temperature to minus yesterday and skip today. That will be a better approximation of the changing rate of today, which is weird, right? Okay. But now with Taylor series, we can explain this. I will write down what I just wrote. You can also go back to the video. If you do this, this equals that. Okay? But we still have the arrow. H squared, H cubed, dot, 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 dot. Note that when H is small, very small, that means H is going to be bigger than H squared, way bigger. For example, 0.1 is way bigger than 0.01. It's way bigger than 0.1 to the cube, which is 0.001. So when H becomes extremely small, all these terms after that won't matter that much. All that matters is only this term. Okay. A second way to think about it is, we do have the error estimate of Taylor polynomials. Remember, it's like Rn, that's what we call them. And if you followed my instructions before, you know all these things after that will be roughly all dominated by this thing here. But instead of using f prime prime a, you need to use m. Okay, but either way, we can write it down. That is, this one is going to be this one plus an arrow, and the arrow is roughly a number times h. That's our conclusion. Now let's take a look at this other formula. That thing has fa plus h, so let me just write it down using Taylor polynomials. H squared plus f prime 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 a 3 factorial h to the cube and so on. Fa minus h is another Taylor expansion. You just replace your h by negative h. So fa minus. Everything else stays the same, right? You only replace h by negative h. Okay? Then what happens when you use fa plus h minus fa minus h? Think about it. That means all the terms who share the same sign minus will be gone. What's left is going to be twice of this whenever you change sign. So it's going to be f prime a 1 factorial 1 factorial is just 1. I'm just going to write 1. H, but you have two of them. Plus, you skip this term. The next one is going to be h cubed now. Okay, with some constant, which you don't really care. Still okay? And then all the stuff after that. Now, if we use the error estimate of Taylor polynomial, you just have a h to the cube term here, which is the dominant one. Now, if you divide 2h on both sides, we get the central difference formula. This one, after you divide by 2h, will become a constant times h squared. So as far as you can know, when h goes to 0, this one also goes to f prime a. When h goes to 0, this one also goes to f prime a. So they're as good as each other if you let h goes to 0. But if you look at the arrow, it becomes interesting. Formula 1, the arrow is a constant times h. Formula 2, the arrow is a constant times h squared. Why? Because when you use this one minus this one, the next term actually is gone. So you jump through this next term, go to the next one. The next one is going to have a higher power of h. So this one is h squared. That means what? That means if you take h to be 0.1, the arrow of this one will be a constant times 0.1, but the arrow of this one is going to be a constant times 0.01. Which one is bigger? This is the bigger arrow, because whenever you have a higher power for some small h, this one is way smaller. Good so far? Another thing you think about is here, this. If I reduce my h by a factor of 10, the arrow here is going to reduce by a factor of 10. But if I reduce my h by a factor of 10, the error here is going to reduce by a factor of 100 because it's h squared. If you divide by h by 10, then h squared becomes h squared over 100. Good so far. So through the analysis of Taylor series, we found this formula is better. How much better? An order of h better. That means every time you have a 10, I reduce by 100. You reduce by half, I reduce by 4 times. That's really fast convergence, which means your error really reduced dramatically. That's a clever thing to do, and it's all thanks to Taylor series. Okay, so that's the beauty of it. So let's wrap up. This gives us a way to calculate the numerical derivative, and this one equal to this one plus a constant times h. This gives you all the error coming from Taylor polynomial, and this fact tells us when h goes to 0, this one will go to the real derivative. That's what we had before. But now, with some clever design, by canceling things out using symmetry, we have another formula. This one does the same thing. As h goes to 0, this one also goes to the derivative. But this one has a way smaller error because my h is a little bit order higher. Thanks to Taylor polynomial. Okay. Now if you use a computer using data points to approximate the changing rate, you definitely should prefer this one. Okay, because it's a smaller error with the same effort. Now, probably start to wonder, can I be even smarter by designing something really weird? I don't know, like a plus 2h minus 2f a minus h, and maybe using 3f a divided by 3h or something, and then can have another formula, but this time the formula has even smaller error when h is small. The answer is yes. And by your design, you can actually make it even more. You can make it h to the 4, h to the 5th. That means you can design different kind of ways to approximate the derivative using Taylor polynomials. Okay? You can be smart about this. And you can get the order of convergence, which is what we have here, which is the power of this one. You can get the error to be arbitrarily small, even when h is just 0.1, which is not too small. But h to the 0.1 to the cube is going to give you a small error. That is great. You don't have to take h to be way small to get a good approximation. But you have a trade-off. That is, this formula can get really complicated. So in real life, you always want to have a trade-off. It's like, do you want a complicated formula, okay, to give you a really good accuracy with big steps, or would you rather to go with an easier one and just take a very small step? That's your call, okay? When I say small step, that means you need a small h. That means your sample should be very close to each other. For example, if you sample every day for the temperature, you probably want to sample it every hour. But of course, sample it every minute will be even better. Okay. But if you give it a complicated formula, it's okay if you sample every hour or even every day or even every month, and you can still have a really, really, really nice approximation. The trade-off is your formula may become really complicated. You need to use more sample points. Okay. I think that's the level I want to stop about numerical derivatives, because this is really interesting, but you should read more about this, and I just give you just a peek of a very, very big area, which is called numerical analysis. It's basically everything you were trying to do with calculus, not just calculus, but I'm just going to use calculus, okay? You have a way to approximate all the results in calculus. Okay? And of course, if it's approximatable. If the original thing are really bad, there's no way you can approximate. You don't even have a Taylor polynomial, that's fine. Okay? But in general, you can always give people an approximation by being diligent. That is, using something very simple, which is polynomial, but you do a lot of terms to approximate the original thing. And the good thing here is you can always do it with a computer. Okay? How to tell the computer lnx is this? Really difficult. But how difficult to tell the computer to do like 3x plus 6x squared minus 7x cubed plus 6 over 4 factorial x to the 4th? Super easy. So that's why we need this. By the way, a last thing to tease you a little bit. Let me write it down. why can't we just use these numbers? Why can't we just use these numbers to approximate f prime a? Because number one, Taylor expansion. Number two, f prime a is in Taylor expansion. Okay. But then you start to wonder, but f prime prime a is also in Taylor expansion. Does it mean that my f second derivative can also be approximated with some formula here? But of course, that thing won't look like difference quotient anymore. What about the third derivative? What about the fourth derivative? Can I just get them by doing sampling instead of actually going inside and find the formula for fx? And the answer is yes. I will give you this one. You think about how to find all these because all the information are in the Taylor polynomial. It's just like a matter of which one do you want to solve. Okay. To do this one, all you need to do is do fx plus h plus fx minus h minus 2f, oh, let's do a. Minus 2fa divided by h squared. And if you don't believe it, try to do it with x to the cube prime at a equal to 0. We know the answer. The answer is going to be 6. Okay, but then try to do this with h equal to 0.1. That means you are going to take f 1.1 plus f 0.9. Actually, why don't I just do it? Minus 2 f1 divided by 0.1 squared, which give you 1.1 cube plus 0.9 cube, which 2 times 1 to the cube, which is just 1, divided by 0.01. So let me do it quickly. The answer is exactly 6. Why? Because you use the 3 Taylor polynomials, so of course it's going to be exactly the same. That's beautiful. But you can try it with some other things, for example, x to the 4. Then you will have some error. But again, the error is going to be super small. Okay? So actually you can have numerical approximations for any functions and for any order of derivatives thanks to Taylor polynomial, because it gives you a nice relationship between the function itself and all the information contained in the derivative of the function. That means, let me say it again, given a point, this is A, you can know the information about the points around A by just knowing everything happening at A, including the derivative, the second derivative, the third derivative. If you know all the derivatives happening at this single point, you will be able to know everything happens close to it, as long as it stays within the interval of convergence. Okay? If the original function is really nice at like e to the x, the interval of convergence is going to be infinity. That means for e to the x, if you know a single point, you will know everything happens to this e to the x from the beginning of the time to the end of time. For something bad, like this, knowing the information here, you cannot predict very far, but you can still predict probably roughly an interval around here, using all the information, only the information you get from this single point to predict what happens here, as long as they behave regularly. The moment they start to actually become funky, the moment you won't converge, the Taylor series won't converge, then that's the moment you lose the predicting power. Okay, it has something to do with something called a chaos system, but that's not the scope of this class. So that's it. That's all the applications I can give you for Taylor polynomial and Taylor expansion. It's Taylor. I don't know if this is a too strong of argument to say, but I would say Taylor polynomial is probably one of the fundamental tools or concepts in calculus. Like we said in class, calculus deals with continuous stuff. Okay. and it gives you something exact, which means it's an accurate number like E or something. But in real life, especially with computer, if you want to use computer can only give you something discrete. It cannot represent all the number between 0 and 1. It can only represent numbers like 0.000001. But you do have a step, no matter how small the step is, of the numbers computer can represent. Okay. They can represent really many, maybe they can represent a million numbers between 0 and 1, but still it's not continuous. So it cannot give you the exact number. It will give you something called the approximation. It will give you something which is in decimal. And in real life, this one is also decimal, but this one never ends. But in mathematics, but in real life, this one always ends somewhere. So what you're trying to do with Taylor polynomial or any approximation is trying to build a connection between the real world, which is finite, to the imaginary world, which is infinite. Okay, and how to connect these two together? That is actually the idea of sequence and series. Okay, and then Taylor polynomial is another way to connect functions and polynomials, which are way easier to do. Okay, again, polynomial never become a function unless you take infinite many of them. So with this, because polynomial can stop anywhere and you're going to have an error with the error estimate, you can use a computer, okay, to solve a lot of mathematical problems, even though from the beginning they should not be put together. Okay, but we can do it simply because we know how big the error is. Okay, so Taylor polynomial probably serves as the foundation of a lot of numerical method, which means you use a computer to solve calculus problem, which from the beginning should not be feasible because this is infinite and this is finite. Okay, Taylor polynomial give you a lot of designs of how to solve things because it involves all the derivative, and of course the integral, and also Taylor series give you the error estimate. So if you're interested later, maybe you will take a class which is called Math 371. It's called the Introduction to Numerical Method. And there you will probably see Taylor series on a daily basis. So if you plan to take this class, or if you plan to actually to get an applied math major or computational physics, you probably want to really look for a lot of videos or reading materials to help yourself to understand Taylor polynomial, because that's the foundation of this class.